Evaluating limits. Expect a mix of algebraic techniques where direct substitution initially yields the indeterminate form 0 over 0. Factoring. Look for a difference of squares, sum/difference of cubes, or trinomials to cancel out the discontinuity. Example, x minus 8. Rationalizing. Multiply the numerator and the denominator by the conjugate when radicals are present. Change a variable, useful for limits involving fractional exponents. Example, let u equal x over 1 to the power of 1 over 6 to clear denominators. Limits at infinity. Divide every term by the highest power of x in the denominator. Remember, if limit x approaches infinity, px over q over x, and degree p is less than degree q, the limit is 0. If degree p equals degree q, the limit is the ratio of the leading coefficients. One-sided limits and continuity. A function is continuous at x equals c if and only if limit f of x approaches c negative equals limit f of x as x approaches c positive equals fc. Optimization word problem. Set up, define your variables clearly. Write a constraint equation. Example, fixed volume, fixed area, or budget. An objective equation, the quantity you want to maximize or minimize. Substitute, use the constraint to express the objective function in terms of a single variable. Intervals, state the domain explicitly based on physical constraints. Example, x has to be greater than or equal to 0. If it's a closed interval, close bracket A, close bracket B, you must check the endpoints along with the critical points. If it's closed interval, the derivative, differentiate set as at f derived x equals 0 and solve for critical values. Verification, you must prove it is a maximum minimum using either the first derivative test, sign chart, or the second derivative test, where you find if you find the critical points of f and then sub it into the second derivative of f. Curve sketching. So domain and intercepts, find x-intercepts fx equals 0 and y-intercepts f where x equals 0. And then symmetry, check if f negative x equals fx or odd f negative x equals negative fx. Asymptotes, vertical VA, non-removable discontinuity where the denominator is 0. Test behavior from the left and the right, positive, negative, infinity. Horizontal asymptote, evaluate limit as x approaches positive, negative, infinity, fx. Oblique occurs if the degree of the numerator is actually 1 higher than the denominator. Use polynomial long division. First derivative, f derived of x, find critical points. F derived of x equals 0 undefined. Set up an interval chart to find intervals of increase/decrease in local extrema. Second derivative, find potential inflection points when f double derivative equals 0 or undefined. Set up an interval chart for concavity up versus down and confirm p points of inflection where concavity changes sign. Motion along the line. So displacement, st equals d over dt. Velocity, vt, derived turns into, so displacement turns into velocity and velocity turns to acceleration. At rest, vt equals 0. Moving forward/right, vt is greater than 0. Moving backward/left, vt is less than 0. Direction change occurs when vt equals 0 and the sign of the vt changes. Speeding up, vt and at have the same sign, both positive or both negative. Slowing down, vt and at have opposite signs. Total displacement for total distance over an interval t1, t2, find where vt equals 0. Split the interval at those times, calculate the displacement of each segment, and add their absolute values. Lines and planes, so vector, parametric, and symmetric equations. So line in R3, r equals r initial plus td. Plane in R3, r equals r initial plus sa plus tb, or the scalar / Cartesian form, ax plus by plus cz plus d equals 0, where the normal vector is n, which is a, b, c. Finding the scalar equation of a plane. If given 3 points or 2 direction vectors, use the cross product a times b to find the normal vector, then substitute a point to solve for d. Intersection, system of equations. Line and line can intersect at any point, be parallel and distinct, be coincident or be skew, not parallel but never intersecting. Test by checking if the system of parametric equations has no solution. Line and plane can intersect at a point, be parallel to the plane, no intersection, or lie entirely within the plane, infinite intersections. Use the parametric equation of the line and substitute them into the scalar equation of the plane. 3 planes, linear systems. Review the geometric configurations, intersecting at a single point, a line, parallel planes, or formando a triangular prism. Use Gaussian elimination or substitution. Or just regular, And then exponential and logarithmic derivatives. E to the power of x equals ex. And then b to the power of x derived equals bx ln b. And then ln x turns into 1 over x when derived. Trigonometric derivatives, sin x turns into cos x turns into negative sin x, tan x equals sec squared x. Dot product u dot v can also be absolute value of u and absolute value of v times cos theta, and then u1 v1 plus u2 v2 plus u3 v3. If u dot product v equals 0, the vectors are orthogonal, perpendicular. The dot product yields a scalar. Cross product u cross product v yields a vector that is perpendicular to both u and v. So absolute value of u dot cross product v equals u absolute value of u times absolute value of v sine theta, which represents the area of a parallelogram spanned by the 2 vectors. Divide by 2 for a triangle. If u times v or cross product v equals 0, the vectors are collinear parallel. Projection, scalar projection of a on b. So comp BA equals a dot product b over b. And then vector projection of a on b, projection BA equals a dot product b over b squared times the direction b. Work and torque applications. Work equals F times S dot product. Torque equals R times F. So cross product magnitude. So magnitude of T equals magnitude of R, magnitude of F times sine theta. And then point of intersection of 2 lines. Write both lines in parametric form using different parameters. So example S and T. Set x1 equals x2, y1 equals y2, and z1 equals z2 to create a system of 3 equations with 2 unknowns, S and T. Solve for S and T using 2 of the equations. Critical steps, substitute S and T into the 3rd equation. If it holds true, they intersect. Substitute either parameter back into its line equation to find the POI. If it fails, the lines are skew or parallel/distinct. Intersection of 2 planes. 2 non-parallel planes intersect along a line. Set up their scalar equations as a system. Eliminate one variable, example x, to find a relationship between the remaining 2. Example y in terms of z. Let the remaining variables equal a parameter, example z equals t. Express x and y in terms of t to get the parametric equation of the line of intersection. Point of POI of 3 planes, linear systems. Set up an augmented matrix or use systematic elimination. Unique solution, 1 point of intersection. Matrix reduces to a clean identity form. So x equals a, y equals b, c equals c. Geometrically, they meet at a single vertex. Infinite solutions, a line of POIs. You get a row of all zeros, 0 equals 0. Express 2 variables in the terms of the 3rd parameter. No solution, you get an inconsistent statement like 0 equals 5. Geometrically, this forms a triangular prism or 2/3 parallel planes. We already get the distance formula, but distance between 2 parallel planes, pick any random point on plane 1 by setting 2 variables to 0 and solving for the 3rd. Then use the point to plane formula above to find its distance to plane 2. Distance from a point Q to a line with direction D and point P on the line. You already get that equation. Remember logarithmic differentiation, so log bx equals 1 over x times ln times b. B is the base. And then also remember when you're rewriting like something, so like let's say we have log x, it turns into 10 to the power of x. Wait, sorry. That's just ignore what I just said. Vertical asymptote, set qx equal to 0, the denominator. If x equals c, makes the denominator 0, but not the numerator. X equals c is vertical asymptote. Horizontal asymptote, so if degree of px is less than qx, then y equals 0. If degree of px is equal to qx, then the leading coefficient of p over the leading coefficient of q is the horizontal asymptote. Oblique asymptote occurs only if the degree of px is exactly 1 greater than qx. Divide px by qx using long division. Ignore the remainder. The quotient y equals mx plus b is your oblique asymptote. Tangents and non-differentiable anomalies. Horizontal tangent occurs when the derivative of f equals 0 and the function is defined. The slope is perfectly flat. Vertical tangent occurs when fx is continuous, but limit x goes to c. Absolute value of f derived x equals infinity. The graph becomes completely vertical at the exact point. So y equals x to the power of 1 over 3 at x equals 0. Corner occurs when the one-sided limit of the derivative exists but do not match. So limit x goes to c negative, derivative fx does not equal limit x goes to c positive f derivative x. The graph has an abrupt sharp turn. So example, y equals absolute value x at x equals 0. If it's a cusp, when the one-sided limits of the derivative approach opposite infinities. So as x approaches c negative, derivative goes to negative infinity, and limit approaches c positive, derivative goes to infinity, or vice versa. The graphs form a sharp point resembling a wave crest. Example, y equals x to the power of 2 over 3 at x equals 0. And commutative law, u dot product v equals v dot product u. Cross product is anti-commutative, so u cross product v equals negative v cross product u. And parallel proofs show that u cross product v equals 0, or show scalar multiplicity, so u equals k times v. Coplanar proofs show that there are 3 triple scalar products is 0, so u dot product v times cross product w equals 0. This indicates the parallel pipe they form has 0 volume, meaning they lie in the same exact plane. So average velocity, so v average equals s distance over change in distance over change in time. Instantaneous velocity equals velocity, which equals derivative of s, acceleration, and instantaneous is at any specific point. Magnitude of a vector is basically when you just like square it, then root it, and add them together. Unit vector and direction of v, so v equals v of the direction over v magnitude. And then area of a parallelogram equals u cross product v. Symmetric line, so x minus x initial equals d1, which equals y minus y initial over d2, which equals z minus z initial over d3.